Tonight, we are going to sit with a question that has no answer. Not a question that does not yet have an answer. Not a question whose answer is currently unknown, but might someday be found. A question that may be, in a deep and fundamental and possibly permanent sense, unanswerable. A question that sits at the absolute edge of what human knowledge can reach, at the boundary where science itself runs out, where the tools we use to understand the universe cease to function, where the very concepts we rely on to ask questions may no longer apply. What came before the Big Bang? This is the question. And tonight we are going to explore not just the possible answers, which are genuinely fascinating, but the deeper and more disturbing possibility that the question itself may be unanswerable in principle. That the wall we are pressing against when we ask it is not a wall of ignorance, but a wall of physical law. That the universe may be structured in such a way that what came before it, if anything did, is permanently and completely beyond our reach. This is not a comfortable thought. Humans are not comfortable with unanswerable questions. We are a species built for curiosity, for investigation, for the satisfaction of finding out. The idea that there are questions that cannot be answered, not due to our limitations, but due to the structure of reality, is the kind of thing that the mind wants to push past, to find some way around, to refuse to accept as truly final. Tonight we will try to understand why the wall may be real, why the question may genuinely be beyond answering, and why that is not a failure of science, but one of the most profound and honest things that science has ever discovered about itself and about the universe. This is Science for Sleep. And tonight, the subject is the edge of everything. Settle in. Let the body rest, and let us begin at the beginning. Or rather, at the question of whether there was a beginning at all. Before we can understand why we may never know what came before the Big Bang, we need to understand what we do know about the Big Bang itself, and why we are confident in that knowledge. The Big Bang is not a hypothesis in the popular sense of a guess. It is the best supported cosmological framework in the history of science, confirmed by multiple independent lines of evidence that all point to the same conclusion. The universe began in an extremely hot, dense state approximately 13.8 billion years ago, and has been expanding and cooling ever since. The evidence for this comes from several directions. The expansion of the universe was the first piece of evidence. In the 1920s, Edwin Hubble discovered that distant galaxies are moving away from us, and that the farther away they are, the faster they are receding. This is precisely what you would expect if space itself is expanding, carrying the galaxies with it. Run the expansion backward in time, and everything converges to a single point of origin, a state of extreme density and temperature, which is what we call the Big Bang. The cosmic microwave background radiation is the second piece of evidence. In 1965, Arno Penzias and Robert Wilson discovered a faint microwave radiation coming from every direction in the sky with equal intensity. This radiation is the afterglow of the Big Bang itself, the light emitted when the universe was approximately 380,000 years old and cooled enough for electrons and protons to combine into hydrogen atoms for the first time, allowing light to travel freely through space. The specific spectrum of this radiation, its temperature, its slight variations from point to point, all match the predictions of the Big Bang model with extraordinary precision. The abundance of light elements is the third piece of evidence. In the first few minutes after the Big Bang, the universe was hot and dense enough for nuclear fusion to occur. Protons and neutrons combined to form hydrogen, helium, and trace amounts of lithium and beryllium. The Big Bang model predicts specific ratios of these elements based on the density of matter in the early universe. The observed abundances of these elements in the oldest stars and in pristine gas clouds match the predictions to within measurement uncertainties. The large-scale structure of the universe is the fourth piece of evidence. The tiny temperature variations in the cosmic microwave background, discovered by the COBE, MAP, and Planck satellites, with increasing precision, represent the seeds of all the structure we see in the universe today. These small density variations, amplified by gravity over billions of years, grew into the galaxies, clusters, and cosmic web that constitute the observable universe. The specific pattern of these variations, their statistical properties, their angular scale, all match the predictions of the Big Bang model combined with inflation, a period of rapid expansion in the very early universe. The Big Bang is not a speculation. It is the conclusion of a century of observation and theoretical work, confirmed at every turn by new data. But the Big Bang model, for all its success, has a boundary, a wall, a place beyond which it cannot see and beyond which its equations break down. That wall is approximately 10 to the minus 40 3 seconds after the Big Bang. The Planck time. The Planck time is approximately 5.4 times 10 to the minus 44 seconds. This is an inconceivably small interval of time, so small that no physical process we can describe or measure occurs on this timescale. It is the smallest meaningful unit of time in current physics, derived from the three fundamental constants of nature that are most relevant to quantum gravity: the speed of light, which sets the scale for special relativity and therefore for all of spacetime physics; Planck's constant, which sets the scale for quantum mechanical effects; and Newton's gravitational constant, which sets the scale for gravitational physics. When you combine these three constants in the appropriate way, you get a unit of time, the Planck time, and a unit of length, the Planck length, approximately 1.6 times 10 to the minus 35 meters. These represent the scales at which quantum gravitational effects become important, the scales below which our current theories cannot be trusted. General relativity, our best theory of gravity, describes spacetime as a smooth, continuous fabric. It works extraordinarily well at the scales we can probe, from the solar system to the observable universe. But at the Planck scale, quantum mechanical effects become important for gravity itself, and general relativity breaks down. It produces infinities, nonsensical results, predictions that cannot be right. Quantum mechanics, our best theory of matter and energy at small scales, works extraordinarily well from the scale of molecules down to the scale of quarks and beyond. But quantum mechanics, in its standard formulation, does not include gravity. It treats spacetime as a fixed background, not a dynamic entity. At the Planck scale, both theories are needed simultaneously, and neither works in that regime. This is the problem of quantum gravity, one of the central open problems in theoretical physics. We do not have a consistent theory of quantum gravity. String theory and loop quantum gravity are the leading candidates, but neither has been confirmed experimentally, and neither yet provides a complete, testable description of physics at the Planck scale. What this means for the question of what came before the Big Bang is this. The Big Bang model, run backward, describes the universe getting hotter and denser as we approach the origin. All the matter and energy in the observable universe was compressed into smaller and smaller volumes. The temperature was higher and higher. At some point, the temperature and density reach the Planck scale, the regime where quantum gravity is essential. Beyond that point, our equations stop working, not because we have made a mistake, but because the theories we have are not the right theories for that regime. The physics of the Planck era, and of whatever came before it, if anything did, requires a theory of quantum gravity that we do not yet possess. The Planck wall is not just ignorance. It is the edge of the regime where our best current theories apply. What is on the other side of that wall is genuinely unknown, and may be unknowable with any theory we can construct within the observable universe. Here is where the question becomes not just scientifically difficult, but philosophically vertiginous. When we ask what came before the Big Bang, we are assuming that the concept of before makes sense at the Big Bang. We are assuming that time existed before the universe began, and that the universe began at a moment in that pre-existing time, the way an event begins at a moment in the time that existed before it. This assumption may be wrong. Fundamentally, deeply, completely wrong. According to general relativity, time is not a fixed background against which events unfold. Time is a component of space-time, the four-dimensional fabric that general relativity describes. Space-time is not a container that exists independently of the matter and energy within it. It is a dynamic structure that responds to matter and energy, curving in their presence, shaped by their distribution, participating in the physics rather than merely being the arena in which physics occurs. If time is part of space-time, and space-time began at or near the Big Bang, then time itself began at or near the Big Bang. There is no before the Big Bang because before requires time, and time did not exist before the Big Bang. This is a thought that the mind initially wants to reject. Of course, time existed before the universe. How could the universe just start? Something must have caused it. And causes come before their effects. So there must have been a before. But this intuition assumes that time is something separate from the universe, something that exists independently of physical reality and within which the universe is embedded. General relativity says this is not the case. Time is physical. It is part of the universe. When the universe began, time began with it. The physicist Stephen Hawking used an analogy that is imperfect but useful. He asked what is south of the South Pole. The answer is nothing. There is no south of the South Pole, because south is defined in terms of moving toward the South Pole, and once you are at the South Pole, you cannot go further south. The question has no answer, not because we have not explored far enough, but because the concept of south breaks down at the pole. Similarly, what came before the Big Bang may have no answer, not because we have not explored far enough back in time, but because the concept of before breaks down at the Big Bang. Time may simply not extend to a regime before the universe existed. This is one of the deepest and most counterintuitive results of general relativity, and it is one of the central reasons why the question of what came before the Big Bang may be genuinely unanswerable. The unanswerability of the question goes deeper still, because even if there were a before, we would almost certainly be unable to access information about it. The observable universe has a boundary. Not a physical wall, not a region where space ends, but a boundary defined by the speed of light and the age of the universe. Light from the Big Bang has had approximately 13.8 billion years to travel. In that time, even at the speed of light, it can only have travelled a finite distance. Light from beyond a certain distance, the cosmic horizon, has not yet had time to reach us. This horizon is not a feature of our instruments or our technology. It is a fundamental feature of the universe. No matter how powerful our telescopes become, no matter how sensitive our instruments, we cannot see beyond the cosmic horizon. Information from beyond it has not reached us, and, if the universe continues to expand, will never reach us. If there was a before the Big Bang, any information about that before would have had to survive the Big Bang itself and somehow propagate into the current universe in a detectable form. The Big Bang was an extraordinarily violent event. The temperatures and densities involved were so extreme that essentially all structure that might have existed in a previous state of the universe would have been destroyed. The Big Bang acts as a cosmic reset button, erasing the information content of whatever came before. Even if quantum gravity allowed physics to continue smoothly through the Big Bang, even if there were well-defined physics on both sides of the singularity, the information about the pre-Big Bang state would be scrambled and diluted by the exponential expansion of the early universe to the point where it would be essentially undetectable in the current universe. The information horizon and the Planck wall together create a double barrier to knowledge of what came before the Big Bang. Even if the physics existed and could be described, even if time extended backward through the Big Bang in some sense, the information about that era would be inaccessible. This is why the answer to the title of tonight's exploration may be never. Not probably not or very difficult, but the specific, careful claim that the structure of the universe may permanently prevent us from knowing what, if anything, came before. In the 1980s, the physicist Alan Guth proposed a modification of the Big Bang model that has become one of its central components. He called it inflation. The proposal is that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion, growing by a factor of at least 10 to the 26th in a time of approximately 10 to the minus 32 seconds. This sounds like a detail. It is not. Inflation solved several problems with the original Big Bang model. It explained why the cosmic microwave background is so uniform in temperature across regions of the sky that without inflation would never have been in causal contact and therefore could not have reached the same temperature. It explained why the universe appears geometrically flat to extraordinary precision. It explained the absence of certain exotic particles, like magnetic monopolies, that the original Big Bang model predicted should be common. Inflation also produced a specific prediction about the pattern of temperature variations in the cosmic microwave background. The quantum mechanical fluctuations during inflation, stretched to cosmic scales by the exponential expansion, should produce a specific statistical pattern in these temperature variations. This pattern, called the nearly scale invariant power spectrum, was observed by the WUMAP and Planck satellites with stunning precision. Inflation appears to be correct. But inflation has a consequence for the question of what came before the Big Bang that is both fascinating and troubling. The exponential expansion of inflation dilutes everything. Whatever existed before inflation, whatever state the universe was in, whatever structure or information was present, inflation stretches it across a region far larger than our observable universe. Any pre-inflationary structure would be diluted to the point of undetectability. Any signal from before inflation would be stretched to wavelengths far longer than the size of our observable universe, making it essentially invisible. Inflation, in solving the problems of the original Big Bang model, also effectively erased the pre-inflationary history of the universe. It created an information barrier between the pre-inflationary state and everything we can observe, even if there was something before inflation, and even if that something left traces. Those traces would be spread so thin across so large a volume that they would be effectively undetectable in our observable patch. This is deeply ironic. The modification to the Big Bang model that makes it most successful also makes it most impenetrable from the other side. Inflation explains our universe beautifully and simultaneously hides its own origin. The question of what caused inflation, what state the universe was in before inflation began, is therefore even more inaccessible than the question of what came before the Big Bang in the original model. Inflation adds another layer of erasure, another veil over the pre-cosmic past. The picture becomes stranger still when we follow inflation to its logical conclusions. Many models of inflation predict that inflation does not happen everywhere in the universe at the same time. Once inflation starts in a region, it tends to produce more inflationary regions, which produce more inflationary regions in a self-perpetuating cascade. This is called eternal inflation. In eternal inflation, the universe is not a single Big Bang followed by a single expanding universe. It is an endlessly inflating background, a multiverse, within which local regions occasionally exit the inflationary state and undergo a Big Bang, producing what looks from within like an expanding universe with physical laws and initial conditions. Our observable universe would be one of these local regions. If eternal inflation is correct, then our Big Bang was not the beginning of everything. It was a local event in a larger inflationary multiverse that may have been running for an indefinitely long time, or that may not have had a beginning in the ordinary sense at all. This seems to reopen the question of what came before the Big Bang. If there is an eternal inflationary multiverse, then something did come before our Big Bang. The inflationary background existed before our particular exit from inflation and our particular Big Bang. But here is the problem. The inflationary background is almost by definition inaccessible to us. Our observable universe is a local region that has exited inflation. The rest of the inflationary multiverse is still inflating, expanding at an exponential rate, the regions separating from us at rates faster than light can bridge. We cannot receive information from the still inflating regions. We cannot observe the multiverse. We can only see our local bubble, our post-inflationary universe. The eternal inflationary multiverse, if it exists, is as inaccessible to us as the pre-Big Bang state in the original model. It answers the question of what came before our Big Bang in principle. There was an eternal inflationary background, but it does not answer the question in practice, because that background is unobservable. And eternal inflation itself has a beginning problem. Mathematical theorems, specifically the Border-Guth-Vilenkin theorem, show that any inflationary spacetime that has been expanding on average over its history must have had a beginning. Eternal inflation cannot be truly past eternal. It must have started somewhere, somehow. What caused the eternal inflationary background to start? What was the state before eternal inflation began? We are back to the same question, pushed back one level further. One of the most concrete scientific proposals for what might have come before the Big Bang comes from a field called loop quantum gravity, specifically from its application to cosmology, loop quantum cosmology. Loop quantum gravity is one of the leading candidates for a theory of quantum gravity. It approaches the quantization of gravity differently from string theory, trying to quantize the geometry of spacetime directly, describing it in terms of discrete quantum states rather than a continuous smooth fabric. When loop quantum gravity is applied to cosmology, to the evolution of the universe as a whole, it produces a striking result. The Big Bang singularity, where classical general relativity predicts the density and curvature of spacetime become infinite, is replaced by a quantum bounce. In loop quantum cosmology, the quantum mechanical nature of spacetime prevents the universe from collapsing to a true singularity. When the density reaches a specific critical value, the Planck density, the quantum effects of gravity become repulsive rather than attractive. The collapse of the universe is halted and reversed. What would be the Big Bang in classical general relativity is replaced by a big bounce, a moment of maximum density from which the universe expands again. In this picture, our expanding universe may have emerged from the collapse of a previous universe. The previous universe contracted, reached the Planck density, bounced, and began expanding as our universe. The Big Bang is not the beginning, but a moment of transition between a contracting phase and an expanding phase. This is a genuinely scientific proposal. It makes specific predictions. Loop quantum cosmology predicts that there should be subtle imprints of the pre-bounce universe in the cosmic microwave background, modifications to the power spectrum of temperature fluctuations at the largest angular scales. Some researchers have claimed to see hints of such modifications in the Planck satellite data. Others are skeptical. The debate is ongoing, but even if loop quantum cosmology is correct and there was a bouncing previous universe, does this really answer the question of what came before? It answers what was in the previous cycle. But what came before that cycle? Did the cycles go back forever? Or did the first cycle have a beginning? An eternal series of bouncing universes has the same problem as eternal inflation. The Border-Guth-Vilenkin theorem applies to bouncing cosmologies as well. A universe that bounces but expands on average over many cycles still requires a beginning. An eternal series of bounces in which the universe neither grows nor shrinks over many cycles is possible in principle, but is a very specific and seemingly fine-tuned scenario. And even in a bouncing cosmology, the information about previous cycles is largely erased by the extreme conditions at the bounce. The density at the Planck scale destroys essentially all structure. Whatever was in the previous universe is scrambled beyond recovery in the bounce. The previous universe's history is effectively inaccessible to us, even in principle. The bounce may be real. The previous universe may have existed. But we cannot know what it was like in any detail, and we cannot know how far back the bouncing goes, or what started the bouncing. String theory approaches the problem differently. In string theory, the fundamental objects are not point particles, but tiny vibrating strings of energy, existing in a spacetime of 10 or 11 dimensions. The extra dimensions, beyond the 4 we experience, are compactified, curled up into shapes too small to detect. The shape in which the extra dimensions are compactified determines the physical laws of the resulting 4-dimensional universe. Different shapes of compactification give different values for the fundamental constants, different particle physics, different cosmological constants. The number of possible compactifications is estimated to be enormous, perhaps 10 to the 500, each corresponding to a different possible universe with different physical laws. This landscape of possible universes is disturbing and fascinating in equal measure. It means that string theory does not uniquely predict the physical laws of our universe. Instead, it predicts an enormous variety of possible universes, and the question of why we live in this particular one becomes a question about initial conditions or selection effects. Combined with eternal inflation, the string theory landscape produces an astonishing picture. The eternally inflating multiverse is filled with bubble universes, each corresponding to a different point in the landscape, each with different physical laws. Some bubbles have the wrong physical laws for complex chemistry or life. Others have the right laws, and observers can exist within them to ask why the laws are what they are. The answer, in this picture, is a form of the anthropic principle. We observe the laws we observe because those are the laws compatible with our existence. In a multiverse of 10 to the 500 different types of universes, some will have the right laws by chance, and observers will arise in those bubbles. We are in such a bubble. The physical constants of our universe are not uniquely predicted by any deeper principle. They are the constants compatible with our existence in a specific bubble of the landscape. This is unsatisfying to many physicists. It seems to give up on the project of explaining why our universe has the physical laws it does. It explains the laws anthropically rather than dynamically, and it is essentially untestable. The other bubbles in the landscape, the other universes with different physical laws, are separated from us by inflating regions that we cannot traverse or observe. What does this say about what came before the Big Bang? The landscape and eternal inflation together suggest that our Big Bang was a transition from the inflationary phase of our bubble to the post-inflationary phase. Before our Big Bang, our region of space was part of the eternal inflationary multiverse. But what before that means, what the origin of the inflationary multiverse was, is as obscure as ever. String theory has not solved the problem of what came before the Big Bang. It has moved the question to a different level and made it, if anything, harder to answer. In 1983, Stephen Hawking and James Hartle proposed one of the most mathematically sophisticated and philosophically striking responses to the question of what came before the Big Bang. They called it the no-boundary proposal. The proposal uses the mathematical framework of quantum mechanics applied to the universe as a whole, what physicists call quantum cosmology. In quantum mechanics, the state of a system is described by a wave function, a mathematical object that encodes the probabilities of different configurations of the system. Hartle and Hawking asked what the wave function of the universe is and what it tells us about the origin of the universe. To calculate this wave function, they used a mathematical technique involving imaginary time. In ordinary physics, time is real, meaning it appears in equations with a positive real coefficient. But mathematically, it is possible to replace real time with imaginary time, a mathematical trick that transforms the equations of quantum gravity into the equations of a different kind of problem that is in some cases more tractable. When Hartle and Hawking applied this technique to the wave function of the universe, they found something remarkable. In imaginary time, the beginning of the universe is not a singular point, a boundary requiring an initial condition, but rather a smooth, closed surface with no boundary. The universe in imaginary time is like the surface of a sphere, compact and without edges. Just as the South Pole is a point on the sphere of the Earth without being a boundary or an edge, the beginning of the universe in imaginary time is a point without being a boundary. When translated back to real time, this corresponds to a universe that emerges from a quantum state that does not require initial conditions. The universe does not begin at a singular moment with specific initial conditions that must be supplied from outside. It has a natural beginning determined by the quantum mechanical framework itself. The no-boundary proposal is beautiful and elegant. It addresses the question of what came before the Big Bang by dissolving it. There is no before, because the beginning of the universe is like the South Pole, a smooth point without a boundary, without anything preceding it. The concept of before simply does not apply to the beginning of the universe in the same way that the concept of south does not apply to a location at the South Pole. But the no-boundary proposal is not without problems. The translation from imaginary time to real time is not mathematically clean in all formulations. Different ways of performing the calculation give different results for the wave function of the universe. Some formulations predict a universe that is likely to be large and smooth, consistent with our observations. Others predict very different universes. The debate about which formulation is correct is technically involved and not yet resolved. And even if the no-boundary proposal is correct, it does not fully eliminate the question of what came before. It answers it by changing the meaning of before at the boundary, by showing that the boundary does not require anything to precede it. But the question of why the no-boundary initial condition applies, why the universe should be described by this particular quantum state rather than some other, remains. Here is another direction from which the question of what came before the Big Bang becomes more complicated than it first appears. The second law of thermodynamics says that entropy, the measure of disorder or randomness in a system, always increases over time in a closed system. Coffee cools. Ice melts. Ordered structures decay into disorder. The direction of time, the distinction between past and future that is so fundamental to our experience, is associated with this increase of entropy. We remember the past and not the future, because the past is the low entropy direction and the future is the high entropy direction. But the second law of thermodynamics only tells us that entropy increases. It does not tell us why the universe started in a state of low entropy. For entropy to be increasing now, it must have been lower in the past. The Big Bang must have been a state of extraordinarily low entropy. This is actually one of the deepest puzzles in physics. Given the laws of physics, most possible initial states of the universe are high entropy, not low entropy. The probability that the universe began in the specific low entropy state it did is extraordinarily small. Why did the universe begin in such a special state? This puzzle, sometimes called the past hypothesis, points toward the necessity of something about the initial conditions of the universe that requires explanation. The low entropy of the Big Bang is not predicted by the laws of physics. It must be imposed as an initial condition, and the question of why those initial conditions prevailed is genuinely open. Some cosmologists have proposed that the answer lies in what came before the Big Bang. If the universe bounced from a previous contracting phase, the entropy of the previous universe at the point of maximum contraction was low because it was compact, and the bounce gave the new universe a low entropy starting point. But this just pushes the question back further. Why was the previous universe in a low entropy state at the bounce? Others propose that in eternal inflation, the low entropy of our universe is explained by the fact that inflating spacetime is in some sense a low entropy state, and our bubble nucleated from this low entropy background. But the entropy of the inflationary background and its relationship to the entropy of the universe as it produces is a complex and not fully resolved question. The thermodynamic arrow of time, the direction of entropy increase, points backward to the Big Bang as a moment of extremely special, extremely low entropy initial conditions. Explaining those initial conditions, understanding why the universe began in such a special state, may require understanding what came before the Big Bang. And if what came before the Big Bang is unknowable, then the full explanation of why entropy increases the way it does, why time has a direction, may be permanently beyond our reach. Let us consider one more radical proposal, one that is more philosophical than physical, but that deserves mention, because it represents one way of dissolving the question of what came before the Big Bang. The physicist and cosmologist Max Tegmark has proposed what he calls the mathematical universe hypothesis. The proposal is that mathematical existence and physical existence are the same thing. Every consistent mathematical structure exists as a physical reality. Our universe is one mathematical structure among an infinite variety of mathematical structures, all equally real. In this view, the question of why there is something rather than nothing has a simple answer. Mathematical structures simply exist. They do not require a physical medium or a mechanism of existence. The integers exist. Geometric spaces exist. The mathematical structure that describes our universe exists. The existence of mathematical structures is not contingent. It does not need to be explained by something external to mathematics. And the question of what came before the Big Bang becomes, in this framework, a question about the mathematical structure of our universe. Within the mathematical structure that describes our universe, is there a well-defined notion of time that extends before the Big Bang? If the mathematical structure of the universe is such that time begins at the Big Bang, there is no before within that structure. The question asks about something outside the mathematical structure, and the mathematical universe hypothesis says there is nothing outside the mathematical structure. There is no outside. This is a genuinely radical proposal, and it is not universally accepted. It is difficult to test. The claim that every consistent mathematical structure exists physically is not obviously true, and is not obviously false. It is more a metaphysical framework than a scientific hypothesis in the ordinary sense. But it represents one honest and thoughtful response to the question of what came before the Big Bang. The response is, the question assumes there is something outside the universe within which the universe is embedded. There is not. The universe is its own mathematical structure. Questions about what is outside it or before it are like asking what is outside of mathematics. The question has no referent. Despite everything we have discussed, despite the arguments that the question may have no answer, that time began with the universe, that inflation erased the pre-cosmic past, that the Planck wall prevents us from probing the beginning, the question keeps coming back. What came before the Big Bang? It comes back because it is a genuinely deep human question, not just a scientific one. It comes back because the mind resists accepting that anything can simply begin without a cause. Every event we have ever experienced in ordinary life had a prior cause. The desk existed before the person sat down at it. The rain existed before it fell. The star existed before we observed it. Causality. The principle that every event has a prior cause is so deeply embedded in our experience of the world that the idea of something beginning without a prior cause feels like a contradiction. But the universe might not be subject to the same causal structure as the events within it. The principle that every event has a prior cause is a principle about events within the universe. It is not obviously a principle about the universe itself. The universe might be in some sense its own cause, or it might be the kind of thing that does not need a cause. Or it might be that the concept of causation simply does not apply to the origin of the universe in the same way it applies to events within it. These are genuinely difficult philosophical positions to accept. They require giving up an intuition that is very deeply held, but the alternative insisting that there must be something before the universe and that this something must be explicable in terms of prior causes, leads to an infinite regress. If the universe had a cause, what caused the cause? If the cause had a prior state, what preceded that state? You cannot answer the question by positing something before the Big Bang, unless that something has no prior cause, and if something can have no prior cause, why not the Big Bang itself? The question keeps coming back because it is genuinely hard, and because no existing framework completely dissolves it. Every proposed answer either pushes the question back a level or dissolves it by fiat, by saying the concept of before simply does not apply. Neither of these responses is fully satisfying, and perhaps that is appropriate. Perhaps the origin of the universe is genuinely the kind of thing that cannot be fully explained within any framework that the universe itself makes available to us. Perhaps the deepest truth about the beginning of existence is that it is genuinely beyond our reach, not because we have not looked hard enough, but because the universe is structured in such a way that its own origin cannot be seen from within. We have spent time with the scientific arguments for why we may never know what came before the Big Bang. But there is a deeper argument, one that sits below the physics, that is worth considering. The human mind evolved to solve problems on the savannah, to track prey, to navigate terrain, to manage social relationships, to build tools, the cognitive capacities that allow us to do science, to reason abstractly, to construct mathematical frameworks and test them against observation, are extraordinary extensions of these evolved capacities. They allow us to think about things far outside the original evolutionary context, about quantum mechanics and general relativity and the cosmic microwave background and black holes. But there is no reason in principle to expect that the human mind, however extended by mathematics and instruments, is capable of understanding everything there is to understand about the universe. The human brain is a specific physical system that evolved for specific purposes. It has specific limitations. It handles certain kinds of problems naturally and other kinds with great difficulty. The question of what came before the Big Bang may be in the category of questions that exceed not just our current knowledge, but our cognitive architecture. The conceptual tools we have for thinking about causality, time, existence, and nothingness were developed in the context of a universe that already exists, that has time, that has events with prior causes. Applying these concepts to the origin of the universe, to the boundary between existence and non-existence, may be like trying to see with ears or hear with eyes. The tool is not adapted for the task. This does not mean the question is meaningless. It means that our cognitive and conceptual tools may be genuinely inadequate for it, and that no amount of refinement of these tools may be sufficient. We may hit a wall not of physics but of thought, a limit to what the human mind can genuinely understand rather than merely describe with symbols. The physicist Niels Bohr, reflecting on the strangeness of quantum mechanics, is said to have remarked that anyone who is not shocked by quantum mechanics has not understood it. Something similar might be true of the origin of the universe. The full understanding of what the Big Bang means, and whether anything preceded it, may require a mode of understanding that we do not, and perhaps cannot, possess. This is not a comfortable thought. But it is an honest one. There is something remarkable about what we have been discussing tonight. We have been exploring not just what science knows about the beginning of the universe, but what science has discovered about its own limits. Science is an extraordinarily powerful method for understanding the universe. In the past few centuries, it has revealed the structure of matter, the nature of life, the shape of space-time, the age of the universe, the composition of stars, the history of life on Earth, the quantum mechanical behavior of particles. These are achievements of breathtaking scope and depth. But science has also, in the process of making these discoveries, discovered the boundaries of what it can know. The uncertainty principle tells us there is a fundamental limit to how precisely we can simultaneously know the position and momentum of a quantum particle. Gödel's incompleteness theorems tell us there are mathematical statements that cannot be proven within any consistent formal system. The cosmic horizon tells us there is a boundary beyond which we cannot receive information. The Planck wall tells us there is a regime in which our current theories break down, and we cannot be sure what replaces them. The discovery of limits is not a failure. It is one of the most profound achievements of human knowledge. To know clearly what you cannot know is itself a form of knowledge, and in many ways a more honest and reliable form than claiming to know things you do not. The question of what came before the Big Bang sits at the intersection of several of these limits. The cosmic horizon prevents us from seeing beyond the observable universe. The inflationary erasure prevents us from seeing beyond the inflationary phase. The Planck wall prevents our current theories from extending past the Planck time. The possible absence of time before the Big Bang prevents the very concept of before from applying. Science has explored these limits carefully, honestly, and with the full force of its mathematical and observational tools. And the conclusion it has reached is not a definitive no. It has not ruled out the possibility of ever knowing what came before the Big Bang. But it has established that knowing is extraordinarily difficult, possibly impossible, and that the honest answer is that we do not know and may never know. This honest answer is itself a scientific achievement. Knowing the shape of your ignorance is better than not knowing it. Here is something worth sitting with. The possibility that there are questions we cannot answer is, in a specific sense, liberating. If every question had an answer that was in principle accessible, then the universe would be a closed system, something that could be completely described and understood and catalogued. The universe would be, in the end, finite in its mystery. All the secrets would eventually yield. But a universe with genuinely unknowable aspects is a universe that exceeds our capacity to contain it. It is a universe that is in some important sense larger than our understanding of it, and will remain so no matter how much our understanding grows. There is something fitting about this. The universe that produced us, that allowed us to evolve and think and ask questions, is under no obligation to be fully comprehensible to the minds it produced. It is not a puzzle designed for human solution. It is whatever it is, and it has revealed a great deal of itself to our patient investigation, but it may have kept some things permanently in reserve. The origin of the universe, what came before the Big Bang, sits in this reserve, not taunting us, not hiding deliberately, but simply beyond the reach of the tools and concepts that our universe provides for understanding itself. And in the quiet of this kind of night, there is something restful about that. The mystery at the beginning of everything is not a problem to be solved tonight. It is a genuinely open question that may remain open, and in its openness, it reminds us that the universe is larger than our understanding of it. That wonder is a sustainable condition because its object is inexhaustible. We will not know what came before the Big Bang tonight. We may never know. And the sky above us continues its ancient turning, the stars burning their hydrogen, the galaxies drifting, the cosmic microwave background filling all of space with its ancient whisper, indifferent to whether we understand its origin. The universe exists. It began. What came before may be forever beyond us. And that is, in its own strange way, enough. One of the most commonly cited responses to the question of what came before the Big Bang involves quantum mechanics and the concept of the quantum vacuum. In quantum mechanics, the vacuum is not truly empty. Even in the absence of any particles or radiation, the vacuum seethes with quantum fluctuations. Virtual particle-antiparticle pairs flicker in and out of existence on timescales so short that they do not violate the uncertainty principle. These fluctuations are real. They have measurable effects, including the Casimir effect, where two uncharged metal plates placed very close together experience an attractive force due to the restriction of vacuum fluctuations between them. The proposal that the universe emerged from a quantum fluctuation in a pre-existing vacuum sounds appealing. Nothing quantum mechanically is unstable. A vacuum fluctuation of sufficient size and energy could in principle nucleate a universe. Our universe might be one such quantum fluctuation, a bubble of space-time that happened to appear in the quantum vacuum of some prior state. This idea has been developed in various forms by physicists including Edward Tryon, who proposed in 1973 that the universe might have originated as a quantum fluctuation of the vacuum, and Alexander Vilenkin, who developed a model in which the universe tunnels quantum mechanically from a state of nothing into existence. But the quantum vacuum proposal has a serious problem. The quantum vacuum is not nothing. It is a specific physical state governed by specific physical laws with a specific quantum mechanical structure. The quantum vacuum of quantum field theory presupposes a space-time in which the fields live, a set of physical laws that govern their behavior, and a specific vacuum state defined by those laws. If the universe emerged from a quantum vacuum, what was the quantum vacuum a vacuum of? What space-time did it exist in? What physical laws governed it? These questions do not dissolve the original problem, they push it back. Instead of asking what came before the Big Bang, we now ask what gave rise to the quantum vacuum, what the physical laws governing it were, and where those laws came from. Something from nothing, in the quantum mechanical sense, is not really something from nothing. It is something from a very specific and structured form of something that is called nothing, because it contains no particles. The true nothing, the complete absence of space, time, physical laws, quantum fields, and any kind of structure whatsoever, is not the quantum vacuum of quantum field theory. Whether a universe can emerge from true nothing is a question that physics cannot currently address. It may not be a question that physics can ever address, because physics requires physical laws and physical structures, and asking about what existed before any physical laws or structures is asking about something outside the domain of physics. The cosmic microwave background is our most direct window onto the early universe. It is a snapshot of the universe when it was approximately 380,000 years old, a map of the temperature variations in the primordial plasma at the moment light first travelled freely. The Planck satellite, which produced the most detailed map of the cosmic microwave background to date, revealed the temperature variations with extraordinary precision. The pattern of these variations encodes information about the composition, geometry, and evolution of the early universe. From this pattern, cosmologists have extracted the age of the universe, its matter and energy content, the geometry of space, the spectrum of primordial density fluctuations, and many other quantities. The cosmic microwave background is a triumph of observational cosmology. But it has a limit. It can only tell us about the universe after the moment of last scattering, approximately 380,000 years after the Big Bang. Before this moment, the universe was opaque to electromagnetic radiation. The photons of the cosmic microwave background could not travel freely before last scattering. They were constantly scattered by free electrons in the hot plasma. The cosmic microwave background is, in a specific sense, an opaque wall beyond which electromagnetic observation cannot see. Gravitational waves may allow us to see further. Gravitational waves interact so weakly with matter that they travel freely through the hot plasma of the early universe. If a significant gravitational wave background was produced during inflation or during earlier phases, it should be present today as a background of gravitational waves at very low frequencies. The imprint of these primordial gravitational waves on the polarization of the cosmic microwave background, called B-mode polarization, is one of the targets of current and future CMB experiments. If primordial gravitational waves are detected, they would provide information about the energy scale of inflation, giving us a window into the inflationary phase much earlier than the last scattering surface. This would be a significant advance. But even primordial gravitational waves cannot see back before the Planck time. They too are produced within the universe after its origin. They carry information about the very early universe, but not about what preceded it. The Planck wall remains even for gravitational wave observations. The cosmic microwave background tells us an extraordinary amount about the early universe. It cannot tell us what came before. No electromagnetic observation can, and the question of whether gravitational waves can take us back far enough to see the origin of the universe itself is genuinely open, but most researchers are skeptical. One of the most creative and controversial proposals for addressing the question of what came before the Big Bang comes from Roger Penrose, the mathematician and physicist who shared the 2020 Nobel Prize in Physics for his work on black holes. Penrose proposes a cosmological model he calls conformal cyclic cosmology. The proposal is based on a mathematical observation about the symmetry of physical laws under conformal transformations that change the scale of lengths uniformly. In Penrose's model, the universe goes through endless cycles. Each cycle begins with a Big Bang and ends in the far future when all matter has decayed or fallen into black holes, which themselves eventually evaporate through Hawking radiation. The very far future universe consists only of radiation, no massive particles, only photons and gravitons. A universe containing only massless particles like photons has a remarkable property. Massless particles move at the speed of light and are insensitive to the overall scale of the universe. In a universe with only massless particles, the distinction between large and small loses meaning. The universe has a conformal symmetry that allows the very far future, which in ordinary terms is an infinitely large and cold universe, to be identified mathematically with the very early hot dense state of a new Big Bang. The end of one cycle, mathematically, is the beginning of the next. The infinite future of one aeon becomes the Big Bang of the next. In this sense, each Big Bang is preceded by the previous aeon, and the question of what came before the Big Bang has an answer. It was the previous cycle of the universe. Penrose has made specific observational predictions from this model. He claims that signals from the previous aeon, from the collision of supermassive black holes in the previous universe, should be visible as concentric rings in the cosmic microwave background. He and his collaborators claim to have found evidence for such rings in the data from the MAP and Planck satellites. The claim is controversial. Many cosmologists have examined the same data and do not see statistically significant concentric rings. All find that the claimed rings can be explained by the ordinary statistical fluctuations of the cosmic microwave background without invoking signals from a previous aeon. The debate is ongoing. Conformal cyclic cosmology is creative and mathematically motivated, but it does not fully resolve the question of what came before the Big Bang. In Penrose's model, the cycles may extend backward indefinitely, each Big Bang preceded by a previous aeon. This avoids a beginning, but replaces it with an infinite regress of cycles, each one requiring the previous one. The question of what started the cycling, or whether the cycling is truly eternal, remains. We have now spent considerable time exploring the scientific proposals for what might have come before the Big Bang. Loop quantum cosmology and the bounce, eternal inflation and the multiverse, the string theory landscape, conformal cyclic cosmology, the Hartle-Hawking no-boundary proposal, quantum nucleation from the vacuum. Each proposal is scientifically motivated, each addresses some aspect of the question, and each, when examined carefully, either pushes the question back a level, dissolves the question by changing the meaning of its key concepts, or is observationally inaccessible. None provides a definitive, observationally confirmed answer to the question of what came before the Big Bang. None is likely to in the near future. The fundamental barriers, the Planck wall, the inflationary erasure, the possible absence of time before the Big Bang, remain in place regardless of which model one finds most compelling. The honest answer, which science has arrived at after a century of serious effort, is that we do not know what came before the Big Bang, if anything did. We have multiple speculative frameworks, each internally consistent, each with some theoretical motivation. We cannot currently distinguish between them observationally, and we may not ever be able to. This is not a failure. Science is not obligated to answer every question. It is obligated to be honest about what it knows and what it does not know, and to distinguish carefully between well-supported knowledge and speculative hypothesis. The cosmological models we have discussed are the most sophisticated and serious attempts to address the question that human science has produced. Their failure to provide a definitive answer is a reflection of the genuine difficulty of the question, not a failure of effort or intelligence. The answer that cannot be given is not a placeholder waiting for future knowledge. It may be a genuine terminus, a place where the explanatory reach of science ends. This is a sobering conclusion. It is also, in its honesty, one of the most important things science has ever said. There is a quality to sitting with an unanswerable question that is different from sitting with an unanswered one. An unanswered question holds a kind of tension. The answer is out there somewhere. Patience or cleverness or better instruments will eventually find it. The uncertainty is temporary. This can be motivating. It can also be restless. An unanswerable question is different. If the question genuinely cannot be answered, then there is no tension in not knowing. The not knowing is the permanent condition. You are not failing to find the answer. You are resting in a region of genuine mystery that will remain mysterious. The origin of the universe may be such a region. The Big Bang may be a genuine beginning, before which the concept of before does not apply, from which no information about prior states can propagate, whose own physics is in a regime where our best theories break down. In that case, the question of what came before the Big Bang is a question that meets the edge of existence, not the edge of our knowledge, but the edge of the thing itself. The universe, asked about what preceded it, has no answer to give, not because it is hiding something, but because there is nothing to tell, and perhaps that is the most honest description of the beginning of everything. Not a description, an absence of description, a silence that is not the silence of something hidden, but the silence of something that genuinely was not there. The universe began. Before it, in the simplest and most radical sense, there was nothing. Not even nothing as a state, just nothing. The mind wants to ask what nothing is like. But nothing is not like anything. To be like something is to have properties, and nothing has no properties. It is not dark, because darkness is a property. It is not empty, because empty space is still space, and space is something. Nothing is not anything, and nothing preceded the universe. This is either the most obvious thing in the world or the most incomprehensible, perhaps both. Tonight the sky above you contains the light of stars whose photons have been travelling for years or centuries or millennia. It contains, on a clear dark night, the faint light of the Andromeda galaxy, 2.5 million years old. It contains, invisibly but really, the cosmic microwave background, light that has been travelling for 13.8 billion years and that originated in the hot plasma of the early universe. All of this is the universe. All of this is what has existed since the Big Bang. All of it is inside the boundary of cosmic time, within the era that began when the universe began. What was outside that boundary, before the beginning, if there was a before, is permanently hidden, not by distance, but by the nature of beginnings. The universe began, and in beginning it began time, and before time there is no before. The night sky, for all its depth and richness, for all the billions of light years it contains and the billions of years of history encoded in the light arriving at your eyes, is entirely within the universe. It does not show you the origin. It cannot. The origin is behind the oldest light, behind the last scattering surface, behind the Planck wall, behind the beginning of time itself. And yet the stars are beautiful. The galaxy is real. The universe is extraordinary. Whatever preceded it, if anything did, gave rise to this. 13.8 billion years of cosmic evolution, from the hot, dense plasma of the Big Bang to the present universe of galaxies and stars and planets and life and consciousness and questions. The question of what came before the Big Bang may be permanently unanswerable, but the universe that the question is about is permanently here, permanent in the specific sense that it exists right now, containing you, containing the stars, containing the light that is travelling to your eyes from sources distributed across 13.8 billion years of cosmic history. The origin is hidden. The universe is present. And in the universe's presence, in its extraordinary richness and depth, there is more than enough to contemplate, to wonder about, to be amazed by, without needing to see behind the beginning.